There you go. Okay, so real numbers. Okay, the building blocks of all integers, which are of course real numbers, are its prime factors. Okay, so we're going to have a little bit of a look at prime factors, and so 324, for instance, can be broken down to be 4 times 81, but they're not prime. So we can keep going and say, oh, actually, 4 is 2 squared, and 81's 3 to the power of 4, and they're both prime. So there it is. They're the building blocks that make up 324. Highest common factor, how to find it? Well, we break down the numbers down to its building blocks or its prime factors. Then we pull out the ones they have in common. So let's have a look at 1,176 and 252. 6,196, they're not prime. Almost there. 49's not prime. 4's not prime. I think we're there. Yes, 3 times 2 cubed times 7 squared. 252, that's 463s. We can keep going. 497, no, 9's not prime, neither's 4. There we go. 2 squared, 3 squared, and 7. Now, the reason we do that is, and it's very easy to compare the two and work out highest common factor, because we just want the things they have in common. So, for instance, I'm looking at it, and they both have 7s and 3s and 2s, but what do we pull out? When we're talking about the highest common factor, we always pull out the lowest power. So, yes, they have 2 in both. One's 2 cubed, one's 2 squared. So 2 squared is what we pull out. And 3 to the power of 1 is the lower one, and 7 to the power of 1. So it would be 84. Now, you might be thinking, well, why on earth are we going over this? Well, when you think about it, all this work we've done with algebra, that's exactly what we're doing. Because when you factorise in algebra, you are breaking it down to its building blocks or its factors. And so when you want to find a common factor or highest common factor, you would do exactly the same thing. Which of those parentheses or pieces of algebra do they have in common? So when you factorise, you always remove the lowest power. And we can apply that to algebra. Whenever we factorise in algebra, we always pull out the lowest power. And then there's this other thing called the lowest common multiple. So again, we break it down to its building blocks and write down all the factors, but this time without repeating. So we'll simplify it down to a bit smaller this time. 48 and 15. So 48, 16 threes, 2 to the power of 4 times 3. 15 is just 3 times 5. So we want all the factors that are there without repeating them. That's similar to when we're finding our what? Yeah. Because we don't call it just a common denominator, we call it the lowest common denominator. So in fact it is actually the lowest common multiple we are finding in the algebra. 240 that one turns out to be. Now if we want to find them, knowing our divisibility tests can save a lot of time. And whilst you might be thinking, oh, geez, hang on, how's this relevant to algebra? Let's take quadratics, for instance. One of the questions we say to ourselves is what multiplies together to give the last number? And we don't want to just be trying random numbers. If we know divisibility tests, then we know sensible numbers to pick, things that could possibly go into it. 2, the divisibility test for 2, without cheating and looking at the sheet, of course, it's a very easy one. How do you know if it's divisible by 2? It's an even number. Okay. Divisibility test for 3. Again, don't cheat. Say that again. Very good. The digits add up to be a multiple of 3. 4. Good. Last 2 digits are divisible by 4. Okay, if you want to get in quick for this one, 5. Oh, see, someone could have beat him on that one. Ends in 5 or 0. 6. Right, because 6 can be made up of 2 prime numbers, 3 and 2. So if it's divisible by both of those prime numbers, obviously it's divisible by 6. 7 is a very tough one. I know you're just reading, you're cheating. Yeah. Okay, so you double the last digit and subtract it from the other digits, and the answer should be divisible by 7. Okay? So you double the last digit. Let's find a multiple of 7, which is relatively easy to work with. Give me a multiple of 7. 7, gee, thanks. 49, okay. Let's say 49. Double the last digit, 18. Subtract it from the other digits, which in this case is 4, and we get negative 14, and negative 14 is divisible by 7, so 49 is divisible by 7. Mm-hmm. Yes, if you have to check a divisibility test to see whether 7 is divisible by 7, we're in trouble. Okay. Divisible by 8. Yes, so this time it's the last 3 digits. Divisible by 8. 9. Yeah. And that's because, I guess, 9 being 3 squared, it has a very similar test to 3. So the sum of its digits is divisible by 9. Come on, get in quick. Ends in a 0. Okay. 11's an interesting one.
Sum of odd positions equals sum of even positions or differ by multiple of them.
Very good. Very good. So sum of the even position digits is equal to the sum of the odd position digits, or will differ by a multiple of 11. Okay, I could keep going. There are divisibility tests for 12 and 13 and so on, but let's have a look at... thanks. Let's have a look at fractions and decimals. Now, I'm going to look more interestingly at the converting recurring decimals into fractions. Like, turning fractions into decimals is relatively simple because, of course, the vinculum simply means divided by. And so if you want to work out what 3/4 is, you could say, oh, what's 3 divided by 4? And it comes up with 0.75. Terminating decimals, turning those into fractions are very easy because we use a decimal number system. So we know if it's 0.231, then it's 231 over 1,000. And if that simplifies down, then we'd keep going. But this is the, as I say, the interesting one, converting the recurring decimals into fractions. So I'll choose one which hopefully we know the answer to. 0.6 repeater. You got that one? Let's pretend we don't. Well, let's see. 0.6 repeater is not 0.6666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666666. I could be here all day. In fact, we keep going infinitely. I'm going to let x be 0.6 repeater. That's what we want to find. So x is, in fact, 0.66666666666666666, and so on. 10x would be 6.6666666666666, and so on. But now we can do a subtraction, and all that repeating part will disappear, and we get 9x is 6. X is 6 over 9, which is 2/3. All right, now, so the basic idea there is we let x be what we're trying to find, and then we create a multiple. What sort of multiple? Depends on how many numbers are recurring. So if we transfer this idea through to 0.81 repeater, which is, of course, 0.81, 81, 81, 81, 81, and so on, we'll let x be 0.81, 81, 81, 81, 81, 81. If I multiply by 10 here, no good, because then I'd get 8.18181818. No good, I want 81, 81, 81, 81. So I need to multiply by 100 in this case to move that decimal place 2 spots. And then the same idea will work. We'll do a subtraction, and we get 99x is 81, 81 and 99, which of course simplifies down to be 9 on 11. But of course, sometimes not all the digits are recurring. Something like this, 0.327 repeater, which is 0.3272727272727, and so on. I'll use the same idea. X is 0.327272727272727. There are 2 numbers repeating, so I will multiply by 100, and I get 32 0.72727272727, but that's okay. The 2727272727 lines up. That will still subtract. So if I do a subtraction, I get 99x is 32.4. Well, we don't normally write fractions with a decimal on top, so multiply top and bottom by 10. We get 324 on 990, and that's 18 on 55. Okay, that is the method that in the syllabus they like you to have a look at. What a waste of time. As I say, not how I would do it. Takes too long. Maths is about patterns, okay? So let's have a look at these again. 0.6 repeater ended up being 6. 6 was the number that was recurring. Over 9, well, there's one number recurring, so I'll use 1/9 on the bottom of the fraction. Okay? Which becomes 2/3. What, you say? So 0.81 repeater. 81, because 8 and 1 is recurring. On the bottom, I put 2 9s, not 18, 2 9s, 9 and 9, because there are 2 numbers recurring. That pattern will work every time. So 0.4 repeater, 4 over 9. 0.62, where both of the digits are repeating, 62 over 99. Why waste all that time when you can just go bang, there's the answer. It's 9 over 11. Okay? So if I now have something like 0.7134 where all the digits are repeating, well, that's all right. 7134 over 9999. 4 numbers repeating, 4 9s on the bottom. I think that simplifies down. Yes, it does. There we go. What about the number where it's not all repeating? Watch this carefully. The top of the fraction was 324. How do I get 324? The numbers after the decimal place is 327. But the 3 is not repeating, so I subtract it. Okay? So 327 minus 3. I get 324 on top. On the bottom, I put 990. Why? 2 numbers are repeating, so I put down 2 9s. One number is not repeating, so I put down 1 0. Now, it would be stupid to put the number 0 at the front of the number, because that would be meaningless. So obviously, it goes at the end of the number. 2 9s, 1 0, 990. There's our number. Okay, 18 on 55. So using that idea, if I have 0.1096 repeater where only the 9 and the 6 are repeating, that'll be 1086 on the top, because it's 1096 minus 10, over 9900. 2 numbers repeating, 2 numbers not repeating, which simplifies down to be that.
So what if the repeating numbers were smaller than non-repeating numbers?
Give me an example.
Like 108616161. Because that gives you a negative number.
Okay. 10861 and just the 6 and the 1 repeating. So that will be 10,861 minus 108 over 99000. It will never be bigger, because the first number is you're writing down everything after the decimal place, and then you're just taking away the ones not repeating, so that will always be a smaller number. So you shouldn't get that problem. Yep. Okay, so that's 2A.